On number 2 in the free response, we need to sketch some curves and then eventually we're going to find the area. So we have two curves. We have r1 equals 1 plus cosine theta, and we have r2 equals 1 plus sine theta. So the first part of this question asks us to label the intersection points and a couple of other specific points. So first let's graph these. So 1 plus cosine theta and 1 plus sine theta are both cardioids. And they're going to look the same, except the 1 plus cosine theta is oriented horizontally, 1 plus sine theta is oriented vertically. Since the coefficients on both of these are the same, you know they're going to intersect the origin, and that their far points are going to be the sums, which are 2 in both cases. So let's draw this first one. We're going to have something going on like this for 1 plus cosine theta. So since these numbers are equal, we have the little cusp at the origin. Your far point is the sum of those two. So sine theta is going to look exactly the same, except it's going to be oriented vertically, and it's going to reach 2 over here. So remember that these are going to hit at 1 and negative 1 all around for their the vertical component of the cosine one and the horizontal component of the sine one. So we're going to have something like this. Okay. So we have two graphs here, and they have a couple of intersection points. We have one intersection point here. We have another intersection point down here. And technically we have a third intersection point at the origin because both of them do touch the origin. So we have 3 intersection points, but let's figure out what their coordinates are. So one of them is going to be the origin. So the tricky part about doing this algebraically is that the origin would not show up by just setting these two things equal to each other, because they both reach the origin at different thetas. So you're not really going to find that one, but we do have that point. So intersection points, we have the origin. The origin you can just claim is r equals 0, because you can't really write the origin as a polar coordinate point because it could be any theta. We could figure out what they are for each, so let me do that real quick. So we actually have the point 0. So we would think for the first one, when is this 0? It's 0 whenever cosine theta is negative 1. That's when theta is pi. And what about this one? This is whenever sine theta is negative 1, which would be 3 pi over 2. So those 2 points are both the origin. So that's where those intersect. To get these other points of intersection, we can set them equal to each other. So if we say 1 plus cosine theta has to equal 1 plus sine theta, that means cosine theta equals sine theta. We can get rid of the 1's from both sides. And that means tan theta equals 1. Where does tan theta equals 1? That's when theta equals, so we'd have pi over 4 and 5 pi over 4. You can see that aligns well because we have pi over 4 and then it's opposite 5 pi over 4. So what are these actual points? Well, to figure out the r's, we could just plug those into either equation. So the r for pi over 4, cosine of pi over 4 is square root of 2 over 2, just like sine of pi over 4 is square root of 2 over 2. So the r is 1 plus square root of 2 over 2. And our theta was pi over 4. And the last point down here, what's the r there? Well, that's when theta is 5 pi over 4. Cosine or sine of 5 pi over 4 are just negative root 2 over 2. So we would get 1 minus square root of 2 over 2, 5 pi over 4. So those are our 3 intersection points for this graph. So we were also asked to list the intersection points as well as a couple of other points. So first we have, where is theta equal to pi over 2 on R1 and theta equals 0 on R2. So on R1, when theta equals pi over 2, we would have 1 plus cosine of pi over 2. Cosine of pi over 2 is 0. So that's this point right here. Because pi over 2 is straight up, and it matches, it crosses through 1 like I had originally drawn. So that's that point on the graph. What about theta equals 0 on R2? Well, R2 is this one, 1 plus sine theta. Theta equals 0 should give us sine of 0, which is 0. 1 plus that should give us 1. And again, that's right here, where I had originally drawn the graph. Remember, theta equals 0 is straight to the right. So those are those two extra points that they wanted you to label. So the second part of this problem is find the area in the first quadrant, which is contained by both curves. So on the picture here, let's think about where this is talking about. This is talking about the area right here. So it's in the first quadrant only. So we have the axes that we have to bound ourselves by, and inside both curves. So inside this part and this part. So this shaded area, that's what we want to find the area of. So the problem with doing this is that when you do your normal area integral formula, you need a radius. But we have two different functions that are bounding our area in different places. So we'd have to do this in 2 steps. Or you could consider, if we draw this line directly through, and it doesn't quite look like it because I'm drawing this by hand, but that line of pi over 4, 45 degrees, would cut this area exactly in half. So really we only need to do the area of one of these, and each of these, either the top half or the bottom half, only has one of the functions as its bound, not both. So we could just do one of them and double it, and that's going to be the easiest way to do that. So our area is going to be double our normal formula, which is 1/2 the integral of r squared. So in this case, because our area, regardless of which one we choose, is going straight down to 0 each time, we don't need to subtract another because we're not doing an area, between 2 curves or anything. So we can just pick one and run with it. So just in terms of making the integral a little bit simpler, I'm going to choose the cosine one to do. So the cosine one is this section up here, because that's on this graph. So that would go from pi over 4 to pi over 2. And the graph was 1 plus cosine theta, but we have to square that, r squared. Squared d theta. So evaluating this integral would give us the area of this whole thing, because remember, we're doubling just the top half in this case. So the 2 and the 1/2 cancel out like you might expect. So we get pi over 4 to pi over 2. 1 plus cosine squared, if you FOIL that out, you're going to get 1 plus 2 cosine theta plus cosine squared theta, d theta. So we need to integrate this, and we can do this term by term. We have 1, 2 cosine theta, cosine squared. If you recall from back when we did the trig integrals way at the beginning of the year, when you try to integrate something like cosine squared, it'd be very tough to do in any other way than just using the trig identities. So for that one, you need to use the double angle formula, or the power reduction, whatever it's called, that switches cosine squared to a double angle of cosine. So I'm going to erase this stuff for continuing up there. So this would be pi over 4 to pi over 2, 1 plus 2 cosine theta plus, so remember that cosine squared of theta is 1 plus cosine 2 theta all over 2. So lastly, we can kind of separate or put each one because we do have a constant already. This is 1/2 plus half cosine 2 theta. 1 plus 1/2 would give us 3/2. Plus 2 cosine theta plus 1/2 cosine 2 theta. Alright, now everything is easily integrable, antidifferentiable, so we can do the antiderivative. We're doing this with respect to theta, so 3/2 just becomes 3/2 theta. The antiderivative of cosine is sine, so we have plus 2 sine theta. Excuse me. And the antiderivative of cosine 2 theta is sine 2 theta, but we'd have to divide by 2 because of the chain rule or use substitution. And we already had a 1/2, so we're actually going to have 1/4 sine 2 theta. And we're going from pi over 4 to pi over 2. So now we can just start plugging in all of our numbers here, and we'll see what we get. Now, this one is going to involve a lot of weird numbers, but it will be able to be simplified a little bit. So when we plug in pi over 2, 3 over 2 times pi over 2 would give you 3 pi over 4. Sine of pi over 2 is 1, so this is just plus 2. And when we do sine of 2 theta, 2 times pi over 2 is pi, and sine of pi is 0, so that term disappears. So now we need to subtract when we plug in pi over 4. 3/2 times pi over 4 would be 3 pi over 8. Sine of pi over 4 is root 2 over 2, times 2 would just give you square root of 2. And sine of 2 theta, 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1, so we just get plus 1/4. So now we just need to simplify that a little bit and we're done. So we can combine 3 pi over 4 and 3 pi over 8 because those have this pi's on top that will make that a little bit easier. So 3 pi over 4 minus 3 pi over 8 would be 3 pi over 8. So we have 3 pi over 8. This square root of 2 is not going to be able to combine with anything, and we have it subtracted, so I'll just write that there. And then we have plus 2 minus 1/4. 2 is 8 over 4, so we're doing 8 over 4 minus 1 over 4, so we get plus 7 over 4. And you could combine the 3 pi over 8 and 7 pi over 4 common denominator also, but I think on the answer key for this, they left it like that anyway. So this expression right here gives us the total area in the first quadrant and under those two graphs.